Hello everyone, myself Vishal Saure.
Myself Sanjosh Khabri. Today I welcome you in today's session. We are diving into one of the most powerful tools in transport phenomena, the navier equation. We'll see how this equation governs the fluid flow over a circular tube, annular regions, and over flat plates. Crucial steps in engineering applications. So let's get started.
The navier equation is essentially Newton's second law applied to a fluid motion. It expresses the balance of the force acting on a fluid element.
So we'll start with the first question, which is flow through circular tube. So the figure of the question is as this. So here in the question we are given that the flow is downward and it's a laminar flow. And the tube length is L and radius is R, and the constant density with a rho and viscosity with a mu. So our conditions are like this. The pressure is equal to Pz as pressure is changing only in the z direction, and V theta is 0, Vr is also 0, and Vz is equal to Vz in terms of R, because near at R equal to the radius of the shell, the velocity will be downward, and pressure is changing as Pz. V theta is 0, Vr is equals to 0, and Vz is equals to Vzr. So the boundary conditions at that is equals to 0 is to P0, and so the different form of equation of motion are So the different forms of equation of motion are first rho dv by dt is equals to minus delta t minus delta dot r plus rho g. And the second one is rho dv by dt is equals to minus delta t plus mu del square v plus rho g. The third one is rho dv by dt is equals to minus del p plus mu del square v. The first equation is the general form, and the second equation is where rho and mu are constant. And the third one, rho and mu are constant, and it is a combined pressure form. There are three forms of navier equation. First is Cartesian coordinate system, second is cylindrical system, and the third one is spherical coordinate system. In this question, we will be using the cylindrical coordinate system. Into del Vr by del T plus Vr into so rho multiplied by del Vr by del T plus Vr del Vr by del R plus V theta by R del Vr by del theta plus Vz del Vz by del Z into del Vr by del Z minus V theta square by R is equals to minus del P by del R plus mu into del by del R 1 by R del by del R into dr plus 1 by R square del square dr divided by del theta square plus del square Vr by del Z square plus minus 2 by R square del V theta by del theta plus rho gr and Vz is to Vz into R. So this is the R equation of motion. Our flow is in only in Z direction, so this equation is of no use for us. So the next equation will be theta 1. Similarly, theta equation of motion is also not useful for us as our fluid direction of flow is in Z direction. So we'll only use the Z direction of equation of motion. Now, then Vz by theta by r del dz by del theta is dz del dz by z is equals to minus del p by del z plus mu into 1 by r del by del r into del dz by del r plus 1 by r square del square dz by del theta square plus del square dz by del z square plus mu into gz. First one. So here is the first term. The first term is Vz by del Vz by del t, as Vz is changing in r direction. This would be steady state, so this term would be 0, and Vr is 0, so this term would be 0, and V theta is 0, so this term would also be 0, and Vz is not changing in z direction, so this term would also be 0. Del P by del Z, pressure is changing in z direction, so this term will be there, and del Vz by del R, Vz is changing in this r direction, so this term would also be there, and del Vz square, del square Vz by del theta square will be 0, as Vz is not changing in theta direction, and del Vz is not changing in z direction, so this term would also be 0. So the only terms remaining would be first one mu 1 by r del by del r del Vz by del of r would be equal to 0, as this is combined pressure over here. 0 this would be 0. Using this equation, this is C naught and del of P by dz is equals to C naught. And del P is equals to C naught into dz del P from 0 to P is equals to C naught into 0 to L. P would be equal to C naught into L. By double integrating this equation, we will get Vz is equals to C naught by 4 mu r square plus C2 ln r plus C3. मतलब वैसे क्या फर्क पड़ता है? there is a logical boundary condition which is at r equal to 0. C2 at r equal to 0, Vz should be finite. So that's why C2 will be 0. So our term is this C0 by 4 mu r square plus C3, and C3 would be equal to minus C0 r0 square divided by 4 mu equals to capital R. By further solving this equation, we get Vz as
So we solve a second question, flow through a annulus by a Navier-Stokes equation. The question is the liquid flow through an annulus. The question is said that the liquid flows in upward direction the influence of the pressure difference and gravity, the influence of a pressure difference and gravity in an annular region between two coaxial cylinders of radii Kr and R. Considering the steady state laminar flow of a fluid and constant density rho and viscosity mu in a vertical tube of length L and R. So our fluid is steady state laminar and our density is constant.